Yeah, welcome learners. In this session, we shall discuss about diameter and radius, of course, of graphs. In the previous session, we have discussed about some concepts like paths, walk, cycles, and connectedness. We shall use these concepts in this session. The concept of diameter essentially tells us how far any two vertices of a graph can be, and to measure this farness or closeness we shall introduce the notion of distance between any two vertices of a graph. You can recall that the length of a path is the number of edges it has. So using the length we shall define the concept of distance, and then we shall use this distance concept to characterize bipartite graphs, and then we shall come back to the concept of diameter and radius, and we shall discuss some relationship between diameter and radius. So we start with the concept of distance. You know that between any two vertices of a graph there can be several paths that join them, and we are interested in those paths which are shortest, which have the smallest length. So the distance between any two vertices u and v of a graph G is the length of a shortest uv path in G. That means the length of the shortest path that joins u and v. We shall use the notation dg uv to denote the distance between two vertices u and v of a graph G. And when the graph G itself is not important or is clear from the context, we shall just write duv. Okay, so suppose you have two vertices u and v which lie in distinct components. That means there is no path connecting u and v, and hence in that case we shall write the distance between u and v to be infinity. That means they are at infinite distance from each other. Let's look at some example. Look at this graph. It has 6 vertices. There are 2 components in this graph, as you can see. The first component, the one component which has vertices v1, v2, v3, v4 and v5. Now look at the distance between v1 and v2. They are adjacent. That means there is a path of length 1 between v1 and v2, and in fact this path is the shortest one. So the distance between v1 and v2 is 1. Similarly, we can see that the distance between v1 and v3 is 2, because the shortest path from v1 to v3 is the path v1, v2 and v3. So this is called this is the distance between v1 and v3. Similarly, you can see that the distance between v1 and v4 is 2. I think I need a mouse. Okay, and now look at the vertex v and any vertex on the cycle in the first component. There is no path from v to any of the vi's, and hence the distance from v to vi is infinite for all I. Now look at this graph. There are mainly 3, just concentrate on the 3 vertices, namely u, v and w. You can see that there are several paths from U to V, and the shortest path is this one shown in red edges. This path has length 2, and hence the distance between U and V is 2. Now look at the vertices U and W. The shortest path from U to W is shown in red edges, which also has length 2, and hence the distance between U and W is also 2. Now just look at the vertices V and W. The shortest path from V to W is this one. It has 4 edges, that means it has length 4. Of course, this is not the only path from V to W. There is one more path you can see, which also has a length 4. So distance between V and W is 2. Now we shall look at a very basic property of distance. You must have studied in your analysis course that a distance function is essentially a metric on a metric space which satisfies essentially 3 properties, and in case of graph also this distance function satisfies these 3 properties. These are: the first is the distance between x and y is always non-negative for all vertices x and y of G. This is trivial because you know that the distance between any 2 vertices is the length of the shortest path between x and y, right? And length is always non-negative, so the dxy is non-negative. The second condition says that the distance between x and y is equal to the distance between y and x for all x, y belongs to Vg. This is also easy. Just consider a shortest xy path, and if you just reverse the sequence of the vertices and edges in this path, what you get? A path from y to x, and of course with the same length. So this proves that the distance between x and y equals to distance between y and x. Now the third property is the distance between x and y is less than or equal to the distance between x and z plus the distance between z and y for all vertices x, y, z of the graph G. This is called a triangle inequality. To prove this, what we have to show is that you just consider any xy path that passes through z. We shall show that such a path would have length at least dxy. So now we prove it. So we picked 3 vertices x, y and z in the vertex set of G arbitrarily, and let us assume that the distance between x and y is L. Now if distance between x and z is greater than or equal to L, then what you have? L is less than or equal to dxz, and which is less than or equal to dxz plus dzy, because from the first property we have seen that the distance between dzy is non-negative, so this holds, right, and we are done. So in this case, another case is that the distance between x and z could be less than L, right? So let dxz be less than L, and then it means that the distance dxz is essentially L minus k for some integer k greater than or equal to 1, right. So now there is some xz path, say p, of length L minus k. That means a path p which connects x and z and which has length L minus k. Now we claim that the distance between z and y cannot be smaller than k, because if it is smaller than k, then there is some yz path, say p dash, which has length smaller than k, and we have the path p which is from x to z and has length L minus k, right, and p dash is the path from z to y which has length smaller than k. So what does this mean? This means that the walk p plus p dash, that means the walk that is obtained by joining the path p and p dash, this is the walk from x to z and from z to y. So this is an xy walk, right. P plus p dash is an xy walk and its length is smaller than L minus k plus k, right, because the length of p is L minus k and length of p dash we have taken less than k. So length of p plus p dash becomes less than L, but this contradicts the assumption that dxy is equals to L. How does this contradict? Because you know that dxy equals to L means that any xy path, including any xy walk, must have length at least L, right. So this is a contradiction, and therefore the distance between z and y must be at least k. Now the result follows from here easily. We have the distance between x and z plus the distance between z and y, which is at least L minus k plus k, which is equals to L, and which is equal to dxy. So this completes the proof. So these are the three basic properties we have seen which are satisfied by a distance function on a graph. Let's now look at some questions. If x and y are two adjacent vertices of a graph G, then so that for any vertex z of G, the distance between x, z minus the distance between y, z, and the absolute value of this is less than or equal to 1. We shall prove it using the triangle inequality, and all these properties we have just seen. We are given that x and y are adjacent, right. So this means the distance between x and y is 1. Now by the triangle inequality, the distance between x and z is less than or equal to the distance between x and y plus the distance between y and z, and which is equal to 1 plus dyz, right. So now if you just take dyz to the left hand side, you will get dxz minus dyz is less than or equal to 1. In the same way, we can show that the distance between yz minus the distance between xz is also less than or equal to 1, and therefore the absolute value of this difference is also at most 1. Okay, so now let's look at one type of graphs known as bipartite graphs. A graph G is said to be bipartite if Vg is the union of x and y for some subsets x and y of G, Vg, right. Second, if x intersection y is empty, and third, every edge of G has one endpoint in x and the other point in y. So any graph that satisfies these three conditions is called a bipartite graph. So when we get two subsets x and y must be non-empty and their union is the whole vertex set and they are disjoint. So essentially they produce a partition of the graph, and that partition has a property that any edge has exactly one endpoint in one of these sets. That means one endpoint lies in one set and the other point lies in a different set. So such a graph is called a bipartite graph, and the sets x and y are known as the partite sets. For instance, look at these graphs G and H. Here you can see that the words in the graph G, you can see that the vertices which are red lie in one partite set and the vertices which are white lie in another partite set. And every edge has one endpoint with red color and the other endpoint with white color. So this is a bipartite graph. Likewise, the graph H is also a bipartite graph. Now look at this graph. You can see that this graph is also bipartite with the partite sets x and y. Every edge has one endpoint white and another endpoint red. We shall write a bipartite graph with partite sets x and y as an x by graph. Now this is a very trivial question about bipartite graphs. If G and H are bipartite graphs, then you can show that their union is also bipartite. You just use the definition and you will get this. Now let's look at this graph. Let's try to find whether it is possible that this graph has any two partite sets or not. So suppose we put the vertex x in one partite set, then the vertices y and z cannot be put in this partite set because they are both adjacent to x, right? They must lie in a different partite set, but they can also not lie in the same partite set because they both are adjacent as well. So this graph cannot be partitioned into two partite sets, and this is not a bipartite graph. You can see that this is a cycle C3, an odd cycle. Now look at this graph. It is the cycle C5, cycle of length 5. Suppose you just put the vertex V1 in one partite set, let's say x, then the vertices V2 and V5 cannot be put in x, right? And let's put them in another partite set y. Now V3 and V4 are adjacent, so they cannot be put in one partite set, but they cannot be put in Y as well, because V3 adjacent to V2 and V4 is adjacent to V5. So V3 and V4 cannot be put in Y as well as in X. So the same problem comes here also. So this graph is also not bipartite. So what we are seen here is that if you just look at any odd cycle, it cannot be bipartite, and in fact it is the absence of odd cycles that determines whether a graph has to be bipartite or not. And now we shall look at a result in this regard. It says that a graph is bipartite if and only if it has no odd cycles. So you can see that there are two statements here. The first statement is, if a graph is bipartite, then it has no odd cycles. And the second is its converse, right? That means if a graph has no odd cycles, then it is bipartite. So we shall prove these statements. First we shall prove, if a graph is bipartite, then it has no odd cycles. So assuming that a graph is bipartite, we have to show that if we consider any cycle, then its length must be odd. Okay, so let G be an xy bigraph, and now consider a cycle C equals to V1, V2 up to Vk, V1 in G. So this cycle has length k, right? There are k vertices, and you know that any cycle on k vertices has length k. Now suppose V1 lies in X, then V2 cannot be in X because V2 is adjacent to V1. So V2 must be in Y, and then V3 cannot be in Y. So V3 must be in X. Similarly, V5 must be in X. So if you just look at any odd indexed vertex in this cycle, that vertex would be in X, because we have chosen V1 to be in X. Now look at the vertex Vk and the vertex, since Vk is adjacent to V1 and V1 already lies in X, so Vk cannot be in X, that means Vk is in Y. So K must be even, and this means that the length of C is even, that is C is an even cycle. So we have proved that a bipartite graph has all cycles of even length, or a bipartite graph has no cycle of odd length. Now we shall prove the converse. So let's assume that G have no odd cycles, and we shall show that G is bipartite. So without loss of generality, we can assume that G is connected, because we have just seen that if any two graphs are bipartite, then their union is bipartite as well, right? So if a graph has a graph is disconnected and it is bipartite, then each of its component must be bipartite. So we can assume that G is connected. Now let's pick any vertex X in Vg. Then for each V belongs to Vg, the distance dxv is either odd or even, right? And now this odd or evenness of this distance gives us the required partite sets of G. We define two sets X and Y in such a way that X contains all those vertices of G which are at an even distance from X, and Y contains all those vertices of G which are at an odd distance from X. Okay. Now, to prove that G is bipartite, we have to show that X and Y are the partite sets of G. So, first thing is that we have to show that X union G must be the whole vertex set VG, and you can see that X and Y are disjoint by definition, and their union is also VG. Now, it remains to show that if you just take any edge of G, one of its endpoint must be in X and the other endpoint must be in Y. So, let us choose any edge UV of G. Assume that U and V both lie in X, and let us see what happens. Both lie in X means the distance dxu and the distance dxv both are even, right? So, let P be a shortest xu path and P dash a shortest xv path. Then, if P and P dash have no common vertex, that means the vertex set of P intersection P dash is empty, then if you just take the union of P plus UV with the path P dash, we get an odd cycle. Why? Because P has length even and P dash also has length even, and both have no common vertex, and the edge UV along with these even lengths makes an odd cycle. So, which is a contradiction, because we have assumed that the graph has no odd cycle. Now, let us assume that P and P dash have some vertex in common. So, now we are interested only in the vertex which is farthest from X. So, let us take W to be the farthest vertex from X that lies in both P and P dash. Can I get mouse? So, that lies in both P and P dash. So, now look at this geometrical figure. We have this vertex X here, and vertex W is farthest from X, right? And P is the path from X to U, which is shown in one part is shown in red and another is in white, and P dash is the path which is from X to W and from W to V, right? Now, if you just remove the portion of these paths from X to W, then what we get are subpaths of P and P dash, which are shown in red, and both these subpaths would have either odd length or even length, right? Because we have subtracted the same length from both, right? So, either both have odd length or even length, hence their union would have even length, and now this union along with the edge UV makes an odd cycle, so which is again a contradiction. Hence the graph, hence the edge UV cannot be in X, right? And the same way you can show that edge UV cannot be in Y as well. That means every edge has one endpoint in X and another endpoint in Y. So XY is a bipartition of G. That means G is a bipartite graph. Okay, now let's come to the concept of diameter. The diameter of a graph is the maximum distance between any two vertices of G, and we shall use the notation diam_G to denote the diameter of a graph. To compute the diameter of a graph, we have to essentially pick any two vertices and so that and just somehow find the maximum distance between these vertices. It is easy to see that the diameter of a complete graph is 1. For instance, one such complete graph is shown here, K6. On the right you can see here. Every vertex is adjacent to every other vertex. So the maximum distance between any two vertices in this graph is 1. That is, its diameter is 1. On the other hand, you can see that the diameter of a null graph is infinite. And in fact, if the graph is disconnected, its diameter would be infinite, because if it is disconnected, it would have at least two vertices at infinite distance, right? Now consider these graphs. The graph on the left has diameter 2, because you just look at the vertex which is at center. We shall define shortly what we mean by a center, but you can see that this vertex is at a distance of at most 1 from each other vertex, and any two non-adjacent vertices have a common neighbor. That means the central vertex is common. So this graph has diameter 2. Similarly, the graph on the right is also has diameter 2. Now look at this graph. You can see that the vertex V is at a distance of 2, at most at a distance of 2 from each vertex, and any two vertices which lie on the outer cycle are at most at a distance of 3, and therefore this graph has diameter 3. 3 is the maximum distance between any two vertices in this graph. Okay, now let's look at the definition of complete bipartite graph. In a bipartite graph, we have seen that every edge has one endpoint in one partite set and another endpoint in the another partite set, right? So in a complete bipartite graph, every vertex in one partite set is adjacent to every vertex in the other partite set, right? So in that case, it is called a complete bipartite graph. For instance, just look at these graphs. The graphs on the left is the complete bipartite graph, where the one partite set has one vertex and the second partite set has two vertices, which are shown in two different colors. And the graph on the right is also complete bipartite. When a complete bipartite graph has m and n vertices in its partite sets, then it is denoted by kmn. So the graph on the left is k12 and the graph on the right is k33. Okay, now let's consider a question. What is the diameter of kmn, the complete graph on m and n vertices? To find its diameter, we shall consider any two vertices and find the maximum distance between them. So any two vertices of kmn can be either in one partite set or they lie in distinct partite sets. So when they are in the same partite set, they have a common neighbor, right, which lies in the second partite set, and in that case the distance between them becomes 2, right? Or in the second case, if the two vertices lie in distinct partite sets, then they must be adjacent. So the distance between them is 1 in this case. In any case, the distance between any two vertices is at most 2, and therefore the diameter of kmn is 2. Let's now find the diameter of the Peterson graph. You know that if you just look at this graph and you just look at any two vertices which are non-adjacent, they have a common neighbor. Just look at any two non-adjacent vertices in this graph, they have a common neighbor. It means that the maximum distance between any two vertices is 2, and therefore this graph has diameter 2. Now let us consider another question. If G is a graph with diameter k, then so that G has an independent set of size at least k plus 1 by 2. So to prove it, what we are given? We are given that G has diameter k, and we have to show that G has an independent size of at least k plus 1 by 2. Independent set means a vertex subset of G where every two vertices are non-adjacent, right? There is no edge in that set. The graph has diameter k. It means that it has at least two vertices, right, which are at a distance of at most k. So let us choose two vertices u and v in such a way that the distance between them is k. And now consider the shortest UV path in G, which is shown here. This path has length k, and hence it has k plus 1 vertices. Namely, these vertices are x1, x2, x3 and so on up to xk and xk plus 1, where x1 is u and xk plus 1 is v. Since this is the shortest UV path, you can see that U has exactly one neighbor on this path, and which is x2. Similarly, x2 has precisely two neighbors on this path, which are x1 and x3. Likewise, you can see that x3 has precisely two neighbors, which are x2 and x4. Thus, x1 and x3 are non-adjacent, which both are non-adjacent to x5, and so on. So we just take the set S equals to x1, x3, x5, and so on. Then the last vertex could be xk or xk plus 1, which depends on whether k is odd or even. If k is odd, then we just consider the last vertex to be xk, otherwise xk plus 1. So this set S has length at least k plus 1 by 2, and which is also independent set. So thus we have found that a graph of diameter k has an independent set of size k at least k plus 1 by 2. Let us consider another question. Let G be an n vertex simple graph with maximum degree n minus 2 and diameter equals to 2. We have to show that the number of edges in G is at least 2n minus 4. Okay, so we are given that the graph has maximum degree n minus 2, right? This means that it has some vertex with precisely n minus 2 neighbors, and let this vertex be u. There are n minus 2 neighbors, but these n minus 2 neighbors along with u only make n minus 1 vertices of G. So G has one more vertex, let's say V. Now the diameter of the graph is 2, which means that the maximum distance between any two vertices must be 2, right? Here V cannot be adjacent to u because all the neighbors of u are already given here, which are n minus 2. So u can only be adjacent to some or all of these neighbors of u. So the neighborhood of V is a subset of neighborhood of u, that is NV is a subset of NU, right? Now if NV equals to NV equals to NU, there is no problem, and that we have the result follows easily. But suppose that NV is not equal to NU, that means there is some vertex, some neighbor of u which is not a neighbor of V. And let's first just consider one such vertex, say W, and then such a neighbor of u must be adjacent to some neighbor of V, right? Otherwise the distance between V and W would be greater than or equal to 3. That means the W and V have a common neighbor. Now we can see there are 3 kinds of edges shown in this figure. The edges due to the neighbors of u, the edges due to the neighbors of V, which are not the neighbors of just the neighbors of V, and the edges which are due to the neighbors of u which are not the neighbors of V. So we have MG is at least the cardinality of NU plus the cardinality of NU minus NV plus the cardinality of NV, and the cardinality of NU is the degree of u, and the cardinality of NU minus NV plus the cardinality of NV is equal to again n du, and which is equal to n minus 2 plus n minus 2, and which is equal to 2n minus 4. Thus, we have proved that the graph has at least 2n minus 4 edges. Okay, now we come to another concept, the concept of eccentricity. So, let G be a graph, then the eccentricity of a vertex V of G is the maximum distance of V from any other vertex in G, and we shall denote the eccentricity of a vertex V by epsilon GV or just epsilon V. For instance, look at this graph. The vertices V1, V3, V4 and V6 have eccentricity 3, because for instance just consider the vertex V1. The maximum distance from V1 to any other vertex is 3. You can see that V1 and V4 is a pair which are at a distance of 3. Similarly, the vertices V3, V4 and V6 have eccentricity 3. Now look at the vertices V2, V5, V7 and V8. The vertices which are shown in red, they are at a distance of at most 2 from any other vertex. So their eccentricity is 2. Now eccentricity gives us the concept of center. The center of a connected graph G is the subgraph of G induced by the vertices of G that have minimum eccentricity, and we shall use the center G to denote the center of G. So center G contains all those vertices which have minimum eccentricity. For instance, in this graph we have seen that the vertices V2, V7, V5 and V8 have minimum eccentricity which is 2, and hence they induce the center of G as shown in the red vertices and edges. Now let us look at some questions. Given a connected graph G, is it necessary that center G is connected? The answer is no. We have one such example. We have one example here. The subgraph shown in red is the center of this graph. You can see that any vertex in this graph, in this subgraph, has eccentricity 3, and you also can see that this center is disconnected. There is no path from one vertex to another, right? That goes through only in this subgraph. So this is a graph which has a disconnected center. Now it is easy to answer what is the center of KMN. You just look at the vertices which have eccentricity 2 or 1. For instance, just when both M and N are at least 2, then the center of KMN is equal to KMN, and when any one of M and N is 1, then the center is just the center contains only one vertex. Okay, now let us look at the radius of this graph. Radius of a graph G, denoted as rad G, is the minimum eccentricity of a vertex of G, and we shall symbolically write rad G equals to the minimum eccentricity, minimum of epsilon V, where V is in Vg. We have seen the concept of diameter as well as the concept of radius. The concept of diameter is the maximum distance between any two vertices, and which can be expressed as the maximum distance between any two, the maximum eccentricity of a vertex of G, right. So this gives us a clue about the relationship between the diameter and radius, and we shall just see. First, let us consider this graph. The vertices which are red have eccentricity 3, right, and the vertices which are green have eccentricity 4, and the vertices which are white have eccentricity 5. So the vertices of maximum eccentricity are the vertices which have eccentricity 5, and hence the diameter of this graph is 5. So you can see here that the radius of this graph is not half of its diameter, and this might be a little surprising because you can see that a graph is not like a circle or a sphere, and although it can be represented geometrically, but it is quite a different kind of geometrical object. The precise relationship between the diameter and radius of a graph is given here, and it says that if G is any graph, then the radius of G is at most the diameter of G, and which is at most twice of the radius of G. The first inequality here is trivial because we have seen that the radius of G is a minimum eccentricity, whereas the diameter is the maximum. So radius of G is less than or equal to the diameter of G. To prove the second inequality, we pick any two vertices U and V in such a way that the distance between them is diameter of G, and such a vertices exist, such a pair exists, and let W be a vertex in G such that the eccentricity of W is equal to the radius of G. Now the diameter of G equal to the distance between U and V, and which by the triangle inequality is less than or equal to duw plus dvw, and which is less than or equal to epsilon w plus epsilon w, because you know that epsilon w is the maximum distance of W from any other vertex, right, whereas duw is just the distance between W and U. So now which is the sum epsilon u plus epsilon w is less than or equal to twice of the radius of G. So thus we have proved that a graph has at most twice of its the diameter of a graph is at most twice of its radius. Now I have some questions for you. Find the center, radius and diameter of a path, a cycle, a wheel graph and a Peterson graph. The next question is, let G be an n vertex simple connected graph. What is the maximum diameter of G if the maximum degree of G is n minus 1? In the second case, the maximum of degree is n minus 2. These questions are easy. The next question is, let G be an n vertex simple graph with maximum degree at most n by 2. Prove or disprove that the diameter of G is at least 3. And the last question, for each n greater than or equal to 3, construct a graph G of order n with diameter of G equals to twice of its radius. So in this session we have discussed the concepts like distance, and we have used this to characterize bipartite graphs. and then we have discussed the concept of diameter, eccentricity, center and radius, and finally we have looked at a relationship between diameter and radius. So this is with this we end this session here.